Imagine machines that don't just do work, but participate in markets. A drone, robot, or vehicle could accept tasks, earn payments, buy services, and follow human-defined rules using decentralized identity, wallets, and smart contracts. Now we're connecting the course threads. Earlier modules gave machines cognition, interfaces, bodies, sensing, energy awareness, and edge intelligence. Project 28 asks the next question. When machines can act in the world, how should they participate economically, safely, transparently, and under human-defined governance? An autonomous machine is more than equipment, but less than a legal person. Its AI agent can make bounded choices, accept approved jobs, collect payment, and spend from a machine wallet on essentials like energy, data, maintenance, or insurance. Identity and reputation help make it trustworthy in a network. But the key is control. Humans define the rules, limits, and accountability. Traditional automation is powerful, but it still depends on people, companies, or software owners to assign work, approve payments, and schedule maintenance. Agent-owned machines change that pattern. A device can earn revenue, pay for energy or compute, request service, and coordinate with other machines through decentralized networks. That creates a feedback loop. Operations generate income, income sustains operations, and the network adapts as demand changes. This is why DePIN matters. Mobility, energy, compute, agriculture, and logistics can start behaving less like managed assets and more like self-sustaining service ecosystems. A machine wallet is the machine's financial operating account, with guardrails. It can receive task payments, compute rewards, or delivery fees, then use approved funds for energy, repairs, insurance, data access, or software updates. Depending on the ecosystem, the balance may include tokens, stablecoins, credits, or vouchers. The safety comes from the policy layer: spending limits, approvals, audit logs, and multi-signature rules. Revenue can also be split automatically into operating budget, maintenance reserve, upgrade funding, and owner dividends, so autonomy remains accountable. In an autonomous marketplace, a machine cannot simply show up and claim it can do a job. It needs a trust passport. A decentralized identifier gives it a persistent identity that can be verified without relying on one central database. Verifiable credentials attach facts to that identity: who controls it, what hardware it has, where it is allowed to operate, and whether it meets safety or licensing requirements. Reputation adds the behavioral layer: uptime, reliability, ratings, dispute history, and maintenance records. Together, these signals reduce impersonation, fraud, and unsafe task matching. The AI operating agent is the machine's executive decision layer. It reads marketplace demand, machine health, location, energy levels, policies, and prices. From there, it decides whether to accept a job, adjust a route, pause for charging, request maintenance, or escalate to a human. The goal is not maximum autonomy. It is bounded autonomy. Human-defined guardrails set forbidden tasks, spending limits, legal zones, safety thresholds, and override points. Advanced agents can also make lightweight local decisions using TinyML or neuromorphic chips, reducing latency and power use while keeping humans in control of the boundary. Robotic service marketplaces turn machine labor into a programmable transaction. A requester posts a job, such as inspection, delivery, cleaning, or charging. The marketplace matches that demand with a machine that has the right capability, location, price, and availability. A smart contract locks in the terms: deadline, payment, penalties, and proof of completion. Funds can sit in escrow while the robot performs the task. Afterward, evidence from sensors, oracles, validators, or humans confirms the result. If everything checks out, payment settles automatically. If not, dispute rules determine what happens next. Completion has to be proven, not just claimed. Machines need evidence that answers what happened, where it happened, when it happened, and whether it met the required standard. That evidence can come from GPS trails, photos, video, sensor telemetry, energy use, timestamps, and completion logs. Trusted hardware and cryptographic attestations make the record harder to fake. Then oracles and validators translate real-world proof into systems that can release payment, trigger penalties, or update reputation. In sensitive environments, the challenge is proving enough without exposing private data. Think of the machine as running a business loop. It finds a job in a service marketplace, then asks, "Can I do this safely, profitably, and with enough energy?" If the answer is yes, a contract locks in the terms and payment. The machine performs the work, records proof of completion, and triggers settlement. But revenue is not just profit. It is routed into energy, maintenance, upgrades, insurance, network fees, and owner returns. That allocation keeps the machine capable of earning again. The result is a repeatable economic cycle. Autonomous maintenance turns repair from an emergency into a budgeted operating loop. A machine tracks its own battery health, motor wear, sensor drift, software state, and environmental stress. When risk rises, it can reduce demanding jobs, book a certified service provider, order parts, or rent diagnostic equipment. Payment comes from funds the machine has already reserved. A smart contract releases that payment only after verified proof of service is logged. The result is fewer breakdowns, higher uptime, safer operation, longer asset life, and more reliable service for customers. Agent-owned machines are most likely to appear first where work is repetitive, measurable, and connected to digital infrastructure. Think delivery fleets, warehouse robots, charging stations, microgrid batteries, farm drones, inspection bots, or cleaning machines. These assets can earn revenue by completing services, spend that revenue on energy and maintenance, and coordinate with nearby systems. The common pattern is not the industry. It is machine work that can be tracked, priced, and improved over time. Economic autonomy is not the same as social independence. If a machine can earn money, accept jobs, buy services, or move through public space, it must operate inside enforceable boundaries. That means clear identity, explicit permissions, spending limits, safety zones, audit records, liability rules, and emergency shutdown. Oversight may come from humans, cities, insurers, fleet operators, or governance councils, depending on the context. The design goal is not to let machines escape institutions. It is to let them participate in society in ways that remain auditable, accountable, and aligned with human values. By 2050, the major shift may not be just smarter machines. It may be machines operating as accountable service networks. A vehicle, drone, harvester, sensor, charger, or data center could pay for power, request maintenance, sell capacity, and coordinate with nearby systems automatically. Humans still define the rules, safety limits, and public goals. But routine settlement and coordination move into the network itself. That could make cities more efficient and remote regions more resilient if we design these machine economies around sustainability, transparency, and shared benefit. The big takeaway is that autonomous machines are not just robots doing jobs. They can become accountable economic actors, verifying tasks, delivering services, proving results, getting paid, and funding their own upkeep. That same pattern now expands outward. Next, we move from machine autonomy to decentralized science, and then to simulation systems that help societies anticipate risk and build resilience.